Hello. In section 8.4, we introduce and talk about the section of trig substitution. So in trig substitution, we are looking for the specific forms. We're looking for some number squared minus x squared, some number squared plus x squared, or x squared minus some number squared. This usually happens under a root, not always. So just because we have a root doesn't mean we have to have trig sub. And just because there's not a root doesn't mean it's not trig sub. So we are looking for these certain expressions. And when we see these expressions, there's a substitution we can make. So the first substitution is if we see the square root of a squared minus x squared, or just a squared minus x squared. Does the square root's not needed? In the case of seeing a squared minus x squared, the substitution we make is x equals a sine theta. The reasoning for this is we can then use the identity that cosine squared is equal to 1 minus sine squared theta. And using that Pythagorean identity, the subtraction will just turn into a cosine. Then for x squared minus a squared, would be under a square root, would not be. We use the substitution x equals a secant theta. Reasoning is for the use of the identity that tangent squared theta is equal to secant squared theta minus 1. So with this subtraction, after we make the substitution, it'll be able to turn into a tangent squared. And for the last form, x squared plus a squared, we use the substitution x equals a tangent theta, again, because tangent squared theta plus 1 equals secant squared theta. So this x squared plus a squared will turn into an a secant squared theta. So first thing to be aware of is that not everything with these square roots are trig sub. Here are two problems that look very similar. One of them is trig sub, one of them is not. So taking a look at them individually, the first problem is -1 to 1 of x times the square root of 1 minus x squared dx. This is a u sub problem. We could use trig substitution, but it'll take longer. If we see a u sub, we should use the u sub. So using the u sub here, u is going to equal 1 minus x squared. du is going to equal -2x dx, or -1/2 du equals x dx. So this will turn into a -1/2 du, and under the square root turns into u, giving us the integral of -1/2 square root u du. And then remembering to change our bounds. When x equals -1, u equals 1 minus -1 squared, which is 0. And when x equals +1, u equals 1 minus 1 squared, which is also 0. We actually don't have any work to do here. When our bounds are the same, the integral evaluates to 0. And we have our integral answer. The reason this is true, that this is going to work out to be 0, is the graph of this looks something like this. And the area that's under the x-axis and the area that's over the x-axis is the same. So they cancel out. leaving us with an area of 0. But all in all, this was a U-sub problem. This other problem, the negative 1 to 1 square root 1 minus x squared, is not a U-sub. I can't rework this 1 minus x squared to be u in any way that will get my integral all into u in a beneficial manner. But if I use the trig sub table, I have this form here. I have the a squared, which is 1, minus x squared. So a, the square root of 1 is 1, a is 1. So I'm going to use the substitution x equals a, or 1 sine theta. X equals 1 sine theta. Dx is going to equal cosine theta. And just like u substitution, I'm going to replace everything out. But now I'm replacing the x with sine theta and the dx with cosine theta d theta. When x equals -1, we near solve for this sine theta. And solving for the sine theta, we get sine is -1 when theta equals -pi/2. And our upper bound of 1 equals sine theta. Theta equals pi/2. So these here will change our bounds, because when we change variables, we need to change our bounds. So we get this is equal to the integral of -pi/2 to pi/2 of the square root 1 minus sine squared theta. It's x equals sine theta, and dx equals cosine theta. We use the substitution because 1 minus sine squared theta is cosine squared. So 1 minus sine squared becomes a cosine squared theta. And we get this integral of the square root of cosine squared times cosine theta d theta. Of course, the square root of cosine squared is just cosine. So all together, we have the integral of cosine squared theta d theta. This we saw a couple sections back that we want to solve with a power reducing formula, where the power reducing formula for cosine squared is 1/2 1 plus cosine 2 theta. Now we can evaluate that integral, and we get 1/2 theta plus 1/2 sine 2 theta. I somehow changed these all to 3s. Should be 2s still. And 1/2 sine 2 theta from -pi/2 to pi/2. Again, when we changed our bounds, these were -pi/2 and pi/2. Somehow changed to 3s, but they are now 2s again. And plugging in our bounds, 1/2 pi/2 plus 1/2 sine of 2 times pi/2 minus pi/2 plus 1/2 sine of -2 times pi/2 from that negative bound. This is a negative bound, -pi/2. And sine of 2 times pi over 2 is the sine of pi. Sine of pi is 0. So this is 0. And for the same reasoning, this is 0. Meaning we have 1/2 of pi over 2 plus pi over 2, which is equal to pi over 2. For similar reasoning, why is this integral from -1 to 1 of the square root 1 minus x squared dx equal to pi over 2? Well, we ultimately have a top half of a circle. This is the square root of 1 minus x squared, going from the bounds of -1 to 1. This is the top half of a circle with radius 1. Top half of a circle with radius 1, that area is 1/2 pi r squared. Radius is 1, this is 1/2 pi. So using our geometry, we get that this answer makes sense. So first thing to note with trig sub, with this first example, is to watch out for u sub, as sometimes it's a quick u sub problem, and when we can't use u sub and we have the right form, we can use trig sub